Okay. So, got it. Share content. Okay. So, Dr. T is so nice that she gives you like a list of things that she's planning on going over in the exam. So we have nomenclature, indicating products, indicating reagents, synthons, which I know you all love synthons. You have to design a multi-step synthesis. So we're going to go over that, multi-step synthesis reactions. And then kind of connected with synthons, a synthetic scheme. So you have to match up stuff. Matching reagents with corresponding synthesis steps, reactivity of alkenes and alkynes, and you got a whole new list of reagents. And then your mechanism. And every week you're going to have a mechanism that you have to understand. So this week it's going to be the keto enol tautomerization. And you're going to be given either acid catalyzed or base catalyzed. So I'm going to start with substitutions and eliminations of halides. So this is question number 16. You are given a structure that looks like this. And you are given a bunch of steps. So 1 is NBS light, 2 potassium, NBS and light again. And, oh, sorry, this is in substitutions and eliminations of halides, which I think is the first section after the review. And then the last step is, once again, your bulky base. So tert-butyl oxide and DMF. So our first step is NBS and light. What happens when we use NBS and light?
We add a bromine and we don't mess with a double bond.
Right. So where does the bromine get added?
The top, I guess.
Yep. Yeah. Yeah. So we call that the allylic position, right? Because it's like adjacent to the alkene. So we do that first.
So if that's the case, it could be on the bottom right as well, right? Just to make sure.
Yeah, it could technically be over here. It's all kind of like the same.
Okay.
So allylic position. And then we're going to do our second step, which is the bulky base. So what is going to happen here? Does anyone want to try it?
It's going to be an E2 elimination reaction that's going to get rid of the bromine and add another double bond across from the other double bond.
Right, so it's going to be an E2 because the bulky base is too large to do like that backside attack. So you can't have an SN2 here. So it's going to end up just eliminating and creating another double bond. There.
And it's on the inside of the ring because it's a 2' carbon, right?
I'm sorry, repeat that?
No, it's going to be inside of the ring as well, the new double bond, because whatchamacallit, it's a 2' carbon that is connected to, not a 3'. Because if it was a 3', wait. Yeah, okay, never mind. Sorry. Yeah.
That's okay.
Yeah.
Yeah, I generally draw my double bonds inside instead of out. I mean,
Because it depends on if it's say it's F or not, right? So
yeah.
Yeah.
So then next step is going to be NBS and light again. So where are we going to add our bromine this time?
bottom right.
The only available carbon left. And then we have our last bulky base. And this time, obviously, it's not going to remove the bromine and create a double bond because there's no room for a double bond. So this is where it's going to do a substitution. So we're going to end up with this.
Hey, Kristen, I'm sorry to cut you off. I think the last one, I think I remember
It
doing
is
this. It was
OME.
like a
It is
yeah, it was
OME.
a yeah,
Sorry.
okay.
It is OME. Yes, thank you. So this one is, it's not going to create a double bond because there's no space, but it will do the substitution.
I have a quick question. So in the
Yes.
last step where it does the substitution, would that be considered the SN2 reaction?
Yes.
Okay,
Mhm.
thank you.
Yes, this is an SN2 here.
On the exam for each step, we have to specify if it's elimination or substitution or whatever.
Probably not.
Okay.
I mean, for your tests, you have some open response questions, but a lot of it is, I think, multiple choice.
Oh, okay.
So, yeah, I mean, if that's like part of the answer, yeah, make sure you select the right one, but
Okay.
I don't think you have to give that if it's a written question.
Okay.
Okay, does anyone have any other questions from this section? Otherwise, I'm going to move on to alcohol dehydration.
Just to put it on your radar, Kristen, is it possible for one of the I think for our final for last semester for OChem 1, we went through E2, SN1, SN2, and E2. We kind of like listed them out and like
Yes.
can we do that at the end just so that I can get like a quick at the end, way at the end?
Yes. Yeah, so actually my plan today was to start with that, and then I went through your homework and I realized how much you actually did. So if we don't have time to do that at the end, I'll just make a separate video, like a short like review of SN2, SN1, Markovnikov, like all of that stuff. It'll only probably be like 15 minutes, but I have a feeling we'll take the full 2 hours today.
Cool.
So
I'm here for all of it. I just, and if you
yeah.
have any questions, I got you. I'm gonna ask you.
Yeah, no, that's good. I'll probably end up making a separate video, but yeah. Okay, so for alcohol dehydration, like the key feature with this is that water is a very good leaving group. And LG stands for leaving group. So, I mean, when we see, say something like, I chose this one because it was not as simple. So like when we see an alcohol group like this, and we're going to react it with concentrated H2SO4, which is an acid, and heat, right? So, well, the first thing that we're going to need to do, actually, is that part of the question? Oh, I think we're actually given the solution here too. Yeah. Let's do purple. So the first thing we're going to have to do is create a leaving group. So in order to create a leaving group, we need to protonate the alcohol. So we're going to have our H2SO4. And we need to draw our electrons. Okay, but the oxygen in the alcohol group is going to snag this hydrogen here, and these electrons are going to move back on here. We need to label our Bronsted base, Lewis base, Bronsted acid, Lewis acid. I said before that this is the acid. So that must make this the base. Now we're going to redraw our picture. So for this step, now we have water instead of alcohol. And the water is basically just going to be like, Sha, I'm out of here. And it's going to leave. And that's all you do for that step. But now we have a positive charge on this carbon. So in order to create like a more stable configuration, we're going to end up having a rearrangement, which is it kind of ends up being like a methyl shift, because what happens is this carbon moves over here. So some people have a little bit of trouble with the visualization of what this looks like. But if you can imagine where it's bonded here, that breaks and just shifts over. So if we redraw, we end up getting structure with five carbons in the ring, and then one sticking out. And this was where we originally had the bond. So it just shifted over one. And now we have a positive charge here instead. So we're going to have a hydride shift. So this was a rearrangement. and this is a hydride shift. Because that positive charge is going to be a lot more stable on a tertiary carbocation. So now we have a tertiary carbocation, and in our solution, we have H2SO4. That's just HSO4 because it's been deprotonated. So it's going to come in and reprotonate itself with that hydrogen that just moved over. And then it will form a double bond. Any questions on how that works?
So my brain
Yes.
isn't letting me see how the positive charge moves when the hydride, or right before the hydride shift happens with the rearrangement. So can you walk through like the mechanism maybe and why the positive charge is there? Or like draw the hydrogens or something so I can just see it.
Oh, right before the rearrangement?
Right after the rearrangement.
Oh, right
'Cause
after the rearrangement. Okay. So, yes, okay. So let's see. I'm going to draw this in black. Because I think kind of keeping track of the carbons is also very tricky with this. So let's make, this one's going to be purple. We'll make that line purple. So this is going to, purple is going to come bond with this carbon. And we'll make this one green. Okay. So when we redraw that, blue is going to be at the top. And we're going to end up having that line there, green, black, this carbon. So we have 1, 2 carbons. Purple. So yeah, that's actually interesting. I feel like they must have rotated it because the positive charge should technically be on the other side. But since it's symmetrical,
Well, no, Kristen, because the methyl shift takes away that positive charge, and then that positive charge moves to the green one. Right?
well, but the green is still having the same connectivity. It's the purple that's actually losing a bond. Yeah, so it would be that one.
Oh, you're right. You're right.
Yeah, but I guess because it's symmetrical, if you just like flip it, it's the same thing anyway. Like you could draw it that way or you could draw it this way. And since our end product has it written like this,
You should just flip it anyways.
you can just flip it. Yeah.
Okay, cool. That makes sense. Thank you so much.
You're welcome. That was a good question. Okay, next stop, synthons. We're gonna do some synthon work. This will take a few minutes. All right. So with synthons, our goal is to identify reactants that form the bond, basically. Right, so in the lectures, I mean, if you can imagine, so we have some molecule or atom that has a negative charge, and it is going to react with some molecule or atom that has a positive charge. They are going to bond together and create something new, right? So the idea is we need to determine where the electrons are going to go in reverse. Like, so if we break this bond, are they going to go on X or are they going to go on Y? So we kind of have to like utilize a lot of the things that we learned in OChem 1 about like molecular stability and electronegativity. So like a good example of this, if we have this, for instance, and we're going to cut it in half right here. Let's try sticking the electrons on here. And then oxygen has a positive charge. So that's not really going to work because this is very high in energy. And if it's just not going to work putting a leaving group on oxygen because it's not really going to react with anything that way. So we need to actually put the electrons on our more electronegative molecule. So in this case, it's going to go on the OH, and that is going to leave this with the positive charge. But we're not done because we need to add a leaving group. And a really good leaving group happens to be bromine. We use it a lot. You can also use iodine or tosylate, which is OTS, although we don't use it really that much in this class. It is mentioned occasionally, but those are both good leaving groups, but you could just use a bromine. Oh, and then we can also stabilize this with some positive ion, usually sodium. All right, so let's do an example. Number 3. Let's say we have this. At least in this problem, we're told to cut it here. So where are our electrons going to go?
The more electronegative ones are the oxygen.
Yep. And then this is going to have our positive charge. But we are not done because we need to stabilize this by adding our leaving group. Bromine. And then these two would react. the electrons would attack that carbon. Bromine would say, see ya. That would make, so if you had to label Lewis base, Lewis acid, which one is the Lewis base?
The
The
anion,
oxygen.
oxygen anion.
Mm-hmm. Yeah. So this is our Lewis base. Let's not forget, it's our electron donor. And then this is our Lewis acid, our electron acceptor. Is that making sense for everybody so far? Any questions?
So just to make sure that like I'm understanding it. So when we like broke that bond with the oxygen and carbon, so the two so that's considered our synthons, right? Where we did the oxygen
Yes.
and like broke it. Okay, making sure.
Yeah, these are our synthons right here. Synthons. Once I added the bromine, this is the synthetic equivalence.
Okay.
So you would also draw this with like a sodium ion to stabilize it. So if we do another one, so we're given this, and let's do orange. We're going to break it here. So let's make our synthons first. So for this one, we're looking at a carbon and a carbon, right? So which direction do you think, let's call this A and this B. Which direction are the electrons going to go to? Are they going to go to A or B?
It has to. Yeah.
Oh.
Go ahead. Yeah.
Sorry.
You could go. It's cool. Yeah.
Oh, I was just gonna say, would it go to A because it's
Yes, it
because
would
of the
go to A.
oxygen on that end?
That is exactly correct. Yeah, so it would go to A.
I'm sorry, Kirsten, wouldn't there also be something to do with the ring as well? Because I remember seeing something on the lecture about that as well. Like, it might not be for this problem in particular, but like if you had to choose one or the other, it might have to do with it being a carbon attached to a ring or something. I don't know. I have to double check, but
Yeah, I haven't actually watched the lectures in a really long time, so
Okay.
I'm not sure what's said on there, but if you happen to find it, you can always like send me a message and
Cool,
ask.
cool.
George,
Yeah.
I think I know what you're talking about. Sometimes when you're on a ring or a double bond, it's going to be an sp2. You can't do
Yeah, that's what it
SN2
was.
on sp2.
Yeah. Yeah.
Oh, right. Yes. So we are going to talk about that later, but I mean, in these examples, they show you where to cut the molecule, but when you
Okay.
have to decide, like for you, let's call this C. If you decide to cut the molecule between B and C, that's not going to work.
Okay.
You can't really do that. And that's because SN2 doesn't happen on the yeah, you can't do it because it's a secondary carbon and SN2 is not really favorable there. It just goes too slow. So we're really looking for like benzylic or allylic or primary. So yes, so these are going to be our synthons. But this case is interesting, right? Because we don't actually have the electrons on an electronegative molecule. They're on a carbon, which is a little awkward. But we actually have resonance here, right? So we can move these electrons into a double bond here. We can move these electrons onto that oxygen, which should have had electrons on it to begin with. And we can redraw this to look like this. And then for our synthetic equivalents, we would just need to draw this. You could draw it either way, but you need to make sure that you're showing it's stabilized. Honestly, I would draw both resonance structures just to be clear.
So when doing this on the test, would we have to show the resonance structures or can we just pick one?
I would definitely show both.
Okay.
Well, I'm getting my voice back. Yeah. I don't know if this would actually be like a free response or if it would be like a multiple choice question, but if you did have to actually draw it out, always draw the resonance structures. Even like in a mechanism problem, you should really show them.
Also, on that same note, Kristen, really quickly, on the short answer part of the actual exam, would there actually be any like short answer things that we have to write out at all, or no? Or is it just doing this pretty much more or less? I don't know.
So I took the class over 2 years ago at this
Oh, okay.
point. So the test has changed a lot. Like for me, it was all free response. So I don't exactly know how they split it up anymore because I don't go look at the exams.
I just took it last semester.
Okay.
And essentially, sometimes you'll have to write an explanation depending on the question. And so sometimes they'll just be like, just explain it. And you'll be like, well, the resonance contributors of this or the the energy of this thing. But it's literally 1 or 2 sentences. Most of the time, you just draw it, make sure you put all the information in your drawings. And that's what I remember most. Yeah. But honestly, it's if you didn't take OChem 1 last quarter, obviously.
Yeah, no, not here. I did.
Honestly, like it's super chill. Like I was super freaked out about the test, but it's super chill. It's like you get a couple multiple choice questions and you get like 2 or 3 free response questions. So it is definitely not all free response, which I would have freaked out if I was in Kristen's. Yeah, it's super chill. Like 3 max.
Okay, cool.
And they're typically short and they're typically mechanism problems.
It's good. I guess it's better to be over-prepared than under-prepared in this case, I guess.
Yeah.
Are there fill-in-the-blank questions on this exam?
No, unless you consider like the free response fill in the blank, but most of that is just working through a mechanism. The like first 5 problems are usually all just multiple choice.
Okay, so it's not like it's going to ask me for spelling, and if I have a spelling error, it's going to like mark it wrong.
No.
Okay, thank goodness.
Well, I just want to put a side note. This is all like memory from last session of OChem 1. So it's not guaranteed that it's going to be the same, but I'm going with Hector, and I'm pretty sure it's going to be similar. But I just want to put that little asterisk right there just in case if it's not the same.
Thanks, Sydney. She's covering me. She's covering me. Sydney's got my back, you know what I mean?
So yeah, so the last part of this would really just be to show that you understand that these electrons are going to come in. I actually want to move this up a little bit so that I can draw it better. So these electrons are going to come in and react with this carbon. This is going to leave. This is your electron donor, so it's your Lewis base. This is the acceptor, so it's the Lewis acid. So that would be the rest of the answer to that question. Okay, now we are going to talk about reverse SN2 reactions. So on these, they don't give you where the bonds are breaking. You kind of have to use what you know now to figure that out. We've got reverse SN2 reactions. So first one we're going to do is number 10. That's a negative charge, positive charge. Okay. So knowing what we know, where do you think we should break the bond? I'm just going to number them 1, 2, 3, 4, 5.
From the third nitrogen.
Yep. We're going to break the bond right there. And the electrons from that bond are going to go into the nitrogen. So for our synthons, we're going to have this. And then a positive charge on that carbon. So for our synthetic equivalents, we just need to add a cation to kind of stabilize this one a little bit. And over here, we need to add a bromine.
I'm sorry, Kristen. So it would still need whatchamacallit, a cation, even though it equals out to a 0 charge. Like the wait, no, never mind. I can't count apparently. Sorry.
That's okay. No, you're fine. Yeah, you should you will want a cation to balance that negative charge at the end there.
Okay. Yeah.
So these would be the synthetic equivalents. And then if you had to draw the reaction, this is going to attack here, this will leave. This is your Lewis base, this is your Lewis acid. You could also call this your nucleophile, this is your electrophile. Yes. And then we're also going to do number 15. Oops. We have H, and C. Now this one might not be as clear. So we're going to have some options. So we could cut it here. We could cut it here. We could cut it here. Or here.
Kristen, would you cut purple because it would have resonance? No.
No.
No,
you-
no, no, no.
No.
Never mind. I'm
Don't.
going with yellow. Final answer.
Yes, go with yellow. That's a good one.
Too soon, Kristen.
That's okay. So we're going to go with this one. So if we cut here, the electrons are going to move on to that oxygen. It is going to look like this.
Can you explain why you chose that one? Sorry, I wasn't paying attention.
That's okay. So we chose that one because oxygen is electronegative, and the electrons are going to be most stabilized going onto the oxygen there and keeping the oxygens together, because there is actually resonance here, because you can do this. So this is also resonance stabilized. I forgot to write carbon. What am I doing now? It's supposed to be CH3. Right, so that is resonance stabilized. And here, is just an excellent place to put a leaving group like bromine. It's also the allylic position because we've got this double bond here. So this will be a very good SN2 reaction. And because we know the bond occurs at this oxygen, if we had to show the reaction, we know that these electrons are going to attack this carbon and bromine will leave. This will be the Lewis base. This will be the Lewis acid. Now, if we cut at some of the other ones, just for the sake of like looking at it, let's try the purple one. So if we cut at purple, which direction? I guess we would probably assume that the electrons would go on the oxygen, right? So we would have positive charge on this carbon, and then a negative charge on this oxygen. And then so that would mean that we would have to put the bromine on this carbon, right, for the leaving group. And this is not, an SN2 reaction is not going to happen here. Because this carbon is sp2 hybridized. Right, it has a double bond to oxygen. So it won't go. So this won't work. Let's try pink. So if we, let's say the electrons go on this carbon, because that's where the oxygens are. So let's say this one has a positive charge. And this one has a negative charge. So this is not too much of an issue on this side. We can add a bromine. That's fine. However, this is just not super stable, especially with carbon already having a double bond to oxygen. Now it's holding on to 2 additional electrons. It's not that it wouldn't go, it's just not the best arrangement. So the orange or dark yellow would still be the best way to go. And then if we were to do the blue one, that would just be awkward. And I don't even know if that one would go either. Let's see.
No, because that carbon has sp2 hybridized, right?
Right. I mean, if the electrons went onto here, and then we had like the bromine on here, but then you have the oxygens, it's just altogether not great. So your best bet is generally to get the electrons on an electronegative atom, whether that be nitrogen or oxygen. Those are going to be your best options. So in this case, this one is the best. So yeah, I think that's it for that section. Multi-step synthesis. Who's ready for multi-step synthesis? I love this section. This is definitely my favorite. Sorry. It's like a puzzle. Let's see. All right, so we're gonna do multi-step synthesis. We're gonna do number 7 first. So number 7, we've got this structure, and we have to get over here. Okay, so first thing we want to notice is which carbon we're adding on. Because the only real difference is the methoxide on our product, and it happens to be at this carbon, which also happens to be in the benzylic position. So that's just a cool thing to take note of. It's in the benzylic position. We can't add a methoxide just like directly. but we can prime that spot to do a substitution reaction by adding what? What do you think we should add?
Bromine.
Yes, bromine. And the best way to add a bromine at this point is
NBS and light.
NBS and light. You're going to use that so many times. NBS and light.
And in this one, we can use Br2 and light as well, right? Since wait, no, you can't because it'll mess with the
Yes.
phenol.
Yeah.
Yeah. Okay.
And that's why you end up using NBS and light so much, because it's easier than worrying about what it's going to mess with.
Okay.
So now, and actually somebody, I forget who it was, but they asked about the plus minus. So you're going to use plus minus when you have a chiral center somewhere, but it could be like added either direction, right? So the bromine could be facing towards us, it could be facing away from us. There's a 50-50 chance that it's going to be either way, and that's why at this point we have to use a plus minus to indicate that it is racemic. Because this is a chiral center. Okay, so at this point, generally with synthesis reactions, we want to kind of try to like get them done in the least amount of steps. So, you know, if you can remember that we have a reagent that just does a substitution reaction here, that's great. And you can just throw that on there and then you're done. Because it will just come in, substitute for the bromine, and now we have the methoxide in the spot where we need it. But if you don't remember that, that is also okay, because you can use different like avenues to get to the product. So another thing that you could do here is you could remove your bromine using like a bulky base. So now you have a double bond there. And you can use the Hg to MEOH, right? Because we're adding methoxide, so we need the methyl there. You could also write CH3OH, both are correct. And then NaBH4, right? Because we're adding in the benzylic position. So this is actually like the more higher priority or Markovnikov position. So yeah, you can just add it that way. So both directions are correct. Sometimes you just forget reagents, so being able to kind of do it in a different way is really helpful. But it's basically a puzzle.
Every time you say that, I think of Dr. Austin and her lectures.
Austin, it's a puzzle. You love this. You're gonna love this.
Kristen, I think in order to love puzzles, you need to just love puzzles in general. And so I do appreciate.
Actually, I hate jigsaw puzzles. I can't stand them.
No, I mean, this is not a jigsaw puzzle, but I see what you mean.
Yeah, I don't like jigsaw puzzles.
This feels more like a crossword puzzle. You know what I mean?
I can get behind like Sudoku.
Yeah, I was thinking more of the Sudoku vibes.
Yeah.
Nah, I can't get with Sudoku. My brain doesn't like little numbers. Remember we had this conversation? I don't understand little numbers. I'm like, I can't add. That's not gonna happen.
You don't have to add with Sudoku though.
Yes, you do. It's like one of the main things in Sudoku. Don't you have to like,
Adding?
yeah,
No,
Have
it's
you ever
not.
done a Sudoku puzzle?
No, it's
Really?
just it's figuring out where all the numbers fit.
Oh,
It's-
clearly I have not done Sudoku properly.
Do I have to
No wonder
draw
you
a
don't like
Sudoku
it.
board?
No, it's okay. It's okay. This is enough Sudoku for me. Thank you. I appreciate all the help though.
That's okay. Okay. I do really like those. My favorite puzzles are the ones where they like give you clues and then you have to like fill in like these little charts. I love those. They're like if Johnny flew an airplane to Tibet, what seat was he in? Because Mary went to Guatemala and I love those puzzles. You have
This
any
is like
idea
one
what
of
I'm
those-
talking about? Yes, they're like logic problems. And they give you like, I don't know, maybe like 10 facts about these different people. And like
Yeah,
things
you
that
get
they
like
did.
a
And
list
you
of
have-
random facts, and then you have to like figure out by a process of elimination.
Yes,
Yeah, I love those.
I love those. They're so much fun.
I think halfway through I would be like, I don't care where Johnny went. Okay, this isn't, and who cares for Johnny? Johnny, just tell me where you went. Like I feel like that's where I would go because I get really frustrated. That's a personal problem, but I like where you're all great.
Well,
You know?
usually like I'll start one and get about halfway through and give up, and then my daughter will come behind and be able to pick up where I left off and finish it and then be like,
Nice.
look. So like between the two of us, we have a really good brain.
All right, so for number 12, we start here.
So can
Go
I
ahead.
ask, can you do it like Dr. T does it? I don't know if you took her lectures, but she goes backwards. And so she goes like, how did you get from this one? And I think maybe that's why I was having such a hard time. I like your way. I'm like, okay, you have to prep it. And then you have to like, do what you need to do in order to finalize. But can you, do you know how to do that? If you don't, that's totally cool.
So sometimes it is easier to go backwards. I find that like later though, in OChem 2, because really when you start adding carbons and things, which I forget what week that is, but at some point your structure will actually become like bigger and longer. And when we start doing stuff like that and changing things from like ketones to aldehydes and carboxylic acids, like that's the point where sometimes I'll start just like working backwards, because you really can't go forward because you don't know what you're doing. But
I
with
found that.
these- Go ahead.
I'm so sorry. I just found that when I was like trying to understand what she was doing, because she broke up the last one into the synthons, and then I kind of like found that the one synthon ends up being the step behind the last step, and then the second synthon, usually like the one with the negative charge, ends up being the like HGOAC, like that, whatever that thing is. It ends up being what is next to the arrow, and then the one synthon that has the positive charge is going to be the one that's like underneath it.
Yeah, I mean, you could definitely do that here. Honestly, like this one working backwards, yeah, it would probably be pretty easy because you're like, okay, well, we're going to break it here. So I know that this spot is going to have a bromine, and you did learn this as a reagent. So you basically just solved it, because then well, I can use NBS and light to put the bromine there, and then I just do a substitution.
So as of now, like technically we're not required to start backwards in this point? Because when I was watching the lectures, um, like they stated, she was going backwards, and she was saying
Mhm.
like when you get your synthetic equivalent, like basically that's the last step before you get like your final answer.
Mhm.
And so I was like, oh, that makes sense. But I was like, it's hard to go back. Like for me, sometimes it's hard to start at the end when I don't know the beginning. But like I like the way you did it too, though. So that makes
Yeah,
sense. 'Cause I
so I
was
mean,
worried about that.
when you have to do the multi-step synthesis, I don't think she has any way of knowing what direction you're actually going in. So I would just kind of favor whatever works best for your brain. I mean, you will be tested on synthons separately. So like if
Okay.
you're able to look at the product here and be like, oh, electrons go on oxygen and throw a bromine on that carbon, then I mean you can just do it that way. But if your brain is not like getting it, you can also analyze it going forward too.
Okay. Yeah, I think going forward is sometimes easier for me as well. So okay, that makes sense. Because I was worried about that. I was like, we're gonna have to go backwards on all these on the test. Like, but that makes sense.
Yeah, I don't think so. I mean, I guess if she has you do like fill in the blank, I would think you could still fill them in your order. I mean, even if she has like the last step first, like you could just work from the bottom and go up. I don't know. I've never taken the multiple choice exam, so I don't actually know how they're formatted, but I know at least for written, I don't think she'd have any way of knowing which direction you're going in. Now for this one is not a synthon one, right? We're just adding a bromine in this position. So we look at the product and we look at where we're starting, and we kind of just want to analyze the differences. So we need to add a bromine in that position. So, I mean, at this point, really like the best way to start is to kind of throw a bromine on it, because that gives us something that we can work with, we can remove, we could swap it. So we are going to do NBS and light. And that does add a bromine on a more substituted carbon, right? Actually, I'm going to redraw this. So now we have something that looks like this. And that's not where we want the bromine at all, right? So let's just get rid of it. So what's the best way to get rid of a bromine?
It depends on if it's 3' or 2', what you use, if you use a bulky base or not.
We're gonna use a bulky base in this case so we can negate an SN2 reaction.
Yeah.
Exactly, yes. Right, because if you end up using this, you're going to get an SN2 reaction, and it's going to look like this. And that's not what we want. No. Okay, so we're going to use a bulky base, which will just come in here and make an alkene on the least substituted carbon, which, let's keep in mind that pH means phenyl group. So we're talking about these big rings, right? So that is not where we're going to end up with a double bond. We're going to end up with a double bond there. So now we have that. And if we glance at our product again, we can see, oh, well, the bromine actually is on the less substituted side of the alkene, and we know a reagent for that. So what's the reagent that we know that does that?
BH3.
What is it?
Isn't it the BH3.THF?
No, because that's
For-
OH. That's for
That's
OH.
for OH.
That's what
yeah.
I thought too.
Got me. Okay.
This would be like an HBr with a peroxide.
Yeah.
Yes,
Isn't it al-
HBr and ROR. ROR.
Huh.
And there you go. Now you have the product.
I know. You already came.
I had that same thought though, because I was like, BH is anti-Markovnikov, but it is for OHs.
Mhm.
Glad I wasn't alone there.
Yeah, and I think in the question it was given racemic, but if it wasn't, you would need to write it down. So this carbon is a chiral center, but we don't know which direction. It's like equally both directions. So you just put a line in plus minus. Because it's equally enantiomers. Oh, there was a bug on me. Okay. So are we good on this one? I have one more. So now we've got number 14. So we're starting there, and we end here. Now this is another one where I guess you could, I mean, if you know enough about cyanide, you could work backwards. This is not as recognizable as like you could chop it here and then, you know, do like a backwards SN2. My brain doesn't work that way for that kind of problem. So I am just going to work forward. So my first step is I'm going to take a look at the product and kind of notice what's different about it. So what's different about it is we are going from an alkane to an alkene, and we are adding a cyanide. So what is our favorite first step?
NBS and light.
NBS and light. Because why not? So we're going to throw an NBS and light on there, which is going to give us a bromine right there, which happens to be in perfect position for a double bond, right? Because if we come in here with a bulky base, that's going to pluck the bromine off, and we're going to end up with a double bond on the least substituted carbons, which is going to be right where we need it, basically. So that's what I'm going to do first. So
I'm sorry, Kristen. I was hearing you, but I didn't process. Can you just repeat that? Like, it's perfect. It's in the perfect spot because of why?
It's in the perfect spot because we can come in there with a bulky base and just like pluck it off like it's a strawberry and it'll leave an alkene on the least substituted, which is what we need, right? Because we have least substituted, and that's like exactly where it is. So if we remove that bromine, we will have an alkene right where we need it. So that is what we're going to do. Oh, that's horrible.
Kristen, in this case, if you were to use a non-bulky base, what would it do? Or would it do the same thing as last time, where we just put an OME in this same spot as the? Okay.
Yeah. Oh, actually, no, because this is a tertiary carbon.
That's what I was thinking.
So it would.
I guess it would go on the side with the phenol, I guess, or would it just stick out where the
Yeah,
bromine?
it wouldn't be able to do that. Hold on 1 second. Do I have any notes here about that?
Yeah.
No, I guess you could use that here also if you wanted to, because this is definitely not a thing. You know, so you can't do that. So you could probably use the non-bulky, the OME, because it's not going to compete with SN2 at a tertiary.
Yeah. Kristen,
But
I have
just
this.
for,
Oh, sorry.
I was going to say just for habit's sake, I would use bulky base. But what were you going to say?
Okay, because I wrote down in my notes. I guess is it okay if I tell you what I wrote down and you tell me if it's correct or not? I guess.
Go ahead. Yeah.
For 3' halides, it says with a bulky base, it gives the anti-Sayetsev product, and with a 3' halide with a non-bulky base, it'll give the Sayetsev product. Is that correct, or am I thinking of it
Yes.
wrong? Okay, yeah.
That is correct. Yeah.
Okay.
Yep. So now we have an alkene here. And oh, look. Oops, I didn't mean to do that. This carbon, we have an allylic carbon. That is very exciting because when we use NBS and lights, that is going to add a bromine there. So now we have a bromine. And we know we can do a substitution reaction just by using cyanide.
So anytime that you want to substitute, the Na plus is like the best route to go?
I wouldn't say anytime you want to substitute. Maybe for this week, it's a very good method.
Mm-hmm.
Because we're doing a lot with SN2 reactions, and bromine is a very good leaving group. And if you notice, what we're adding is usually very like nucleophilic. There's a lot of electrons.
Right.
So they're able to attack that carbon.
Oh, thank you.
You're welcome. I'm always hesitant saying like always or most of the time, just because it never ends up being a good thing to say. But yeah. Okay. So I'm going to move on to cumulative synthesis problems, unless anyone has a specific one in this section that you want me to go over. And this was just the multi-step synthesis section. Okie dokie. So cumulative. Yeah, that's a W. Okay, so number 4. We start with this. We're told plus minus, and that is once again because this carbon is a chiral center, but it's equal parts, both enantiomers. And then we are given the steps, but not the product. So we're told our first step is NBS and light. Our second step is T-butyl oxide. Our third step, BH3THF. And our fourth step is Na plus and peroxide. H2O2, I mean. So first thing is NBS and light. So step 1. Where is our bromine going to end up?
On the allylic carbon.
Yes. That's going to be right there. And we still have to use that plus minus designation here because we still have a chiral center. And it's still equal parts of either enantiomer because the bromine doesn't add specifically. So our second step is T-butyl oxide, which is bulky base. We're going to end up with the less substituted alkene for our bulky base. So it will look like that. Good so far? Okay. And then our third and fourth step happen together. So are we adding OH to the more substituted side or the least substituted side of the alkene?
Least substituted.
That's correct. And then the plus minus comes back because we again have a chiral center. So notice how there's no plus minus here.
Kristen, I had a quick question. So some problems like had the hydrogen written in the final answer and some didn't. Does it really matter if we do that or not? Because I was doing it for a little bit to like signify like syn and anti-addition, but like every time I did it, the answer key didn't either have it or it just kind of omitted the hydrogens. Is it if I write this, are they just gonna assume that I know that? Or
so I think it would specify in the question if she wants you to write all of that in.
okay.
I don't really think that that's like a main focus of this week. So I can't imagine that she's going to have you specify that anywhere. So I
Okay.
think it's just generally like, do you understand it kind of thing.
Okay, thank you.
Oh, okay. I'm sorry you're sick. So chiral center is something we learned about in OChem 1. And it basically just means let's number this 1, 2, 3, 4. So carbon can have up to 4 bonds. right? And so for a chiral center, all of those 4 bonds have to be different for it to be optically active. So I don't exactly understand how it interacts with light. That is kind of like beyond my scope, but the idea is that if you have one enantiomer, so for directions, once you label priority, it could either go this direction, which is R, or this direction, which is S. And these are your enantiomers. If you have equal mix, 50-50 mix, we call that racemic mixture. It's not optically active, but you just have to designate that it's a plus minus. Yes, when drawing aldehyde, very important, always have the H. Yep, that is definitely true. So you can find not racemic centers, you can find chiral centers just by kind of like looking at your different carbons. Like this one that I'm going to make it a different color for a minute, just so you can see. So this one, which is blue, it has hydrogen that you don't see. It has a methyl, has an ethyl group here, and then we have a phenyl group. So it has 4 different groups, and that makes it chiral. And since we don't know what direction everything is pointing, we could have either an enantiomer, so it's going to be a 50-50 mix, or just plus minus, we would call it racemic. Okay, cool. So that's a quick rundown of what that means. So the next one, yes.
Kind of going off the topic a little bit here. So this, I didn't read this anywhere and I didn't see it anywhere in the homework, but it's just something that I've kind of like noticed as a pattern. So when trying to indicate stereochemistry, do you only really write dashed or wedge bonds when you have 2 or more chiral centers? Because I've noticed like in problems where only one chiral center, it's mostly in the planar position, but then if I have 2 chiral centers, I do include the dashed and wedged. Do you know like a general rule about that, or is that just kind of like go as you go per problem?
I think it depends on what the reagent is more so. Like certain things add anti, and for that it tends to become more important. Like I know you'll see a lot more wedged and dashed when you're adding bromine and hydrogen, specifically because of that backside attack, and you have to actually indicate like this one is definitely up and this one is definitely down. But yeah, I don't know if I can make that generalization for that.
Okay, thank you. I just wanted to ask.
Yeah. It might be though, because if you need to show the relationship between the two, it would make sense to show wedged and dashed. I don't know. That is a good question. All right, so number 7, another synthon problem. We are given this. And we need to figure out which direction are we going to break the bond. So let's make this one red. And this one is blue. Are we going to break it red or blue?
Blue.
Blue, yeah.
Yes, blue. Okay, so those would be your synthons. And then this would be your synthetic equivalent. Your electrons are going to attack this carbon. Bromine is going to leave. This is your Lewis base. This is your Lewis acid. And yeah, SN2 is preferred on a primary halide, right? So we've got a primary over here. Whereas if we did it where the red cut is, it's going to compete with an E2. And that's why we can't do that. Just so you can see what would happen. Let's say that carbon has a positive. That has a negative. But the problem here is that instead of this, we might end up with this, which is not what we want. And that is why we cannot go that way. And then I have one more, number 10. So this is where we're starting. This is where we're ending. So we need to add a methoxide, but we can't just change an alcohol into a methoxide, right? And I think the first thing that we could also notice is that you could just like flip this, right? This equals this, or this equals like the other direction also. So like, don't forget that sometimes you can like rotate molecules if you need to. So yeah, so this time NBS and light right off the bat is not going to help us, but we do have an OH, which we could get rid of because it's not helping us at all right now. We can't just like replace a hydrogen with a methyl group. So what is a good way to get rid of an alcohol?
Water.
For the concentrated H2SO4 thing.
Yeah. Yep.
Oh, never mind.
No, yeah, it's cool.
No, you were good. You were good, man. Just listen.
H2.
No hard feelings of giving the right answer.
I mean, you're not wrong. H2SO4 does turn the OH into water, making it a good leaving group. So you're close, but we have to turn it into water. So then it leaves, and we're left with a double bond here. So when we have to add things, bromine is our friend. And when we have an alkene, it's relatively easy to add a bromine. What side do we want it on? Do we want it on the more substituted side or the less substituted side?
Less.
Yes. So how do we add a bromine to the less substituted side?
HBr and peroxide, right?
Mm-hmm.
I have a quick question.
Yes.
So earlier when you were talking about alcohol dehydration and you were talking about creating the leaving group, you kind of showed the arrows of the water actually leaving. But then in this step with the dehydration, you just kind of go from having the alcohol to also having that alkene group. So in a situation like this, if we have to show pushing of the arrows and all that, do we have to show the water leaving, or can we jump from having the alcohol there to ultimately having that alkene group. Does that make sense?
It does make sense, actually. So there's two things happening. Sometimes you're going to have mechanism problems, which we haven't even done like a lot of mechanisms yet. I have a lot more that I wanted to do. But then you also have synthesis problems. So this is a synthesis problem. So we're not showing any of the arrow pushing. It's basically just like product to product to product to product.
Okay, so if she was saying show the mechanisms, then in that case, I would show the water leaving. Okay.
Exactly. Yes.
All right. Thank you.
You're welcome. So we have a bromine. We can just swap it out with the methoxide. So we're going to go ahead and do that. So we've got an A plus and methoxide. Boom, done.
Kristen, really quickly for the what you call it, the alkene that you created from the alcohol, that's specifically an E2 elimination because it's a 1' alcohol, right?
Mm-hmm.
Okay, and if it was 2' alcohol, whatchamacallit, or if it was an alcohol connected to a 2' carbon, it would be an E1 elimination, right? Or am I thinking of it wrong?
With H2SO4, what's the mechanism?
I could have sworn it said something like it's flipped a base, like the type of elimination is flipped based on the if it's 1' or 2' alcohol is connected, or not alcohol, 1 or 2' carbon is connected to the alcohol. I mean,
I'm just not sure if that's true with H2SO4.
yeah.
Yeah, I don't think H2SO4 even qualifies as like E2 or E1 because it's not concerted, so it's definitely not E2.
Okay.
It's you're creating a leaving group, and then removing a hydrogen, which creates the alkene. And sometimes there's shifts, like hydride shifts or methyl shifts. So I don't think that's definitely not an E2.
Okay.
Um,
In the homework, it did say that primary alcohols dehydrate via E2, but they also experience rearrangement every now and then.
Okay.
So I don't know
Okay.
if that.
So I guess it's just something that's not concrete for all, I guess.
I guess. Yeah, let me see if I can.
And then I'm sorry, I had to step out, so I don't know if this was covered or not. But once after that, could you explain, like, is it just because of like because it's an alcohol as the leave or the water as a living group? Since we have an alcohol, you can't just do an SN2 substitution right away off rip. And that's why we have to go through the H2SO4.
I'm sorry, can you repeat your question?
Is it just because of the presence of the alcohol is why we have to go through this multi-step instead of just being able to do an SN2 reaction right off rip?
Mm-hmm.
Okay.
Yeah. Because remember, with the OH, that's not going to substitute with anything. That might react with like another electrophile, like if we were to bring in something that had, but that's not what we're doing here. So we would have to kind of just get rid of it first.
Okay, thank you.
You're welcome. Trying to find E2 real quick. Listen to revisit. I don't know. I will have to get back to you about that.
All right, cool. That's fine, Kristen.
Okay.
Yeah.
Cool. All right. How are you guys with alkyne nomenclature? Do you want to talk about that at all, or do you want me to just get into enol keto stuff?
I know there were people who will very likely watch this that were struggling with it. So
I guess just
With
pick the
nomenclature? Yeah, I can talk about nomenclature.
Yeah, if you could just do one problem with like R, S, and Z and E, that would be
Yeah.
great. Because I know they're gonna include all of it.
Let's
great
do it.
troubleshooting.
I have the perfect one. All right, so alkyne nomenclature. I'm going to do number 12. Okay, I think I drew that correctly. All right.
Yeah, this is a good one.
So our first step is to find the longest chain, right? So that is what we're going to do first. With this one, it's pretty easy to kind of just see that that's the longest chain there. Okay, so we've done that part. Now we need to number so that our highest priority has the lowest number. And this is where it gets a little tricky, right? Because alkenes and alkynes actually have the same priority. So there's some weird rules with this. So I'm going to use two different colors to number two different ways. So I'm going to count from this way: 1, 2, 3, 4, 5, 6, 7, 8, 9. And I'm also going to use red to count from this way: 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, now looking at this, if I look at the red route, our alkyne ends up on 4. And if I look at the green route, our alkene ends up on 3. So that kind of makes the decision for me that I am going to use the green route. Because it is on a lower number. However, if on like the weird chance, right, that the alkyne and the alkene are both on the same number, you use alkene. So if they were both on 3, alkene would still win. But if the alkyne was on a 2, then that one would win. So it's weird. But hopefully that helps. Okay. So I like to make a list of all the things that I have before I write the name down. So we've got a bromo on 2. And I'm going to its configuration. We have an yne on 5. And this is nonane. Or not nonane, but known. We've got an ethyl on 4. And on 7, we've got methyl. Okay, so now we have to go back and kind of add some more information here. So for my bromine, I need to figure out if it is R or S. So to do that, color purple. We don't want to forget that we do have a hydrogen pointing out at us, right? So whatever we find the configuration to be, we're just going to like flip it and make it the other way, right? So bromine should be 1. This is going to be 2. And then the methyl is 3. So that appears, that's going like this direction, right? That looks like an R. But because hydrogen is pointing at us, it's going to be an S. And then I'm going to want to do the same thing with the methyl group on 7. So our hydrogen is already pointing away because the methyl group is pointing towards us. So we just have to do 1, 2, 3. It's going this direction, so that's an R. Now I'm going to look at my alkene and decide if it's E or Z. And Z, if you remember, it's like, isn't 3? Yes, it will be. And I will actually put that in with the full name. You are correct. So E or Z, so Z is like for Z is for like zusammen in German, which means together, and entgegen, which is like again or opposite against. So we want to look at our substituents here. I'm running out of colors, but let's do, okay. So our biggest substituents happen to be this one and this one, right? So they're actually on opposite sides. So because they are on opposite sides, it's going to be E. And now I can kind of stick everything all together, right? So when we actually write out the name, it has to be alphabetical. That's a good way of doing it. Yeah, Zameside. That's how you remember it. That's good. I actually know German, so I don't need a little thing, but yes. I'm gonna actually write that down. So E, either. Okay, so we're going to use the alphabet to put everything in order. So bromo is first. We're gonna have 2S. Actually, I'm gonna run out of room. Let's move this over. 2S bromo. Next is ethyl. We're going to have 4 ethyl. 7R methyl. E comes before Y. We're going to have 3E. And we're going to leave out the E because we are not done. 5. Oh, I forgot the known. There's supposed to be a known right there. And 5, 9. Ooh, enemies. I like that one. Let's do enemies.
For the EN and the YNE, are there like rules with that? Like is the EN only assigned to the double bond and the YN is the triple bond, or is it just dependent on what comes first?
So it's, yeah, EN is the double bond, YEN is the triple bond. I'm pretty sure it's because still alphabet. So even though we stick this at the end, it's still like, at least on the end over there, E comes before Y.
So En will always be, or the majority of the time will be attached to the double bond.
Yes.
Okay.
Yeah, En will always be double bond. It means double bond. The Y and E always means triple bond.
Okay.
Yeah.
It's part of the functional groups. And so even like as we go through like the ketone and stuff, like that's a functional group. So like ENE, there's alkane, alkene, and alkyne. And each of them are just really basic, like one, no double bonds, a double bond, and then the triple bond. But yeah, so just nomenclature stuff in case I don't know when the last time you took alkane was, but yeah. Nomenclature functional groups, sorry.
Okay. So does that kind of clear up some of the questions with the alkaline nomenclature? We feel
Yes.
about it? Okay. I'm going to talk about patternization. And that's probably all the time I'll have left for today, because I have another meeting after this. So let's addition of H2O. So you learned this week that even though we love using this to add H2O, it's not reactive enough with an alkyne. So we needed to learn another way, which is the H2O, HgSO4, H2SO4, right? Which is going to do Markovnikov addition.
And Kristen, really quickly, I'm sorry. Does it matter which order you put those three in, or does it not? I don't know. Like if you put the mercury one first, would it matter or no?
That is a good question. I don't. Well,
Because for me, I put HGS.
I don't see it in this order. Sorry, what's that?
Oh, because in the homework we had to type it in like, oh, which reagent makes this. I put HeSO4, H2SO4, and H2O, and it took it, but I'm not sure if that, if it's technically not correct or not. I don't know. Yeah.
I think it would be fine because I think it's just kind of like in a mixture together.
Oh, okay.
So it's probably okay to write it that way.
All right.
Just just the homework, the exam isn't like the homework. The homework has you type it out, but usually the exam has it already out.
Oh, okay.
It usually will already have the, unless she's asking for it, but it'll already be pre-typed out, and you just have to it's a drop-down box or something.
Oh, okay.
But in case it's different, then yeah, don't. But it might be. But yeah, it was every time last semester quarter it was a drop-down. You never had to type it out or anything.
All right, cool.
I was gonna say in her office hour too, she said she's gonna have a list of reagents for us.
Oh yeah, duh. Right. Okay, cool.
Which is amazing. That's so cool.
Yeah.
Heck yeah, there's so many now.
There's gonna be so many more. Okay, so let's start with this. This is actually kind of highlighted in your notes. But it's just going to be good to know because I think it was also in the homework, like this question. to draw out the actual mechanism. So we're going to look at the actual mechanism of this. So the first part, you end up having Hg2 plus. Gosh, I forget why. 1 second. The Hg2 plus, yes, and by the way, it is a stronger acid. So it reacts with water to kind of dissociate. So you end up with Hg2 plus and SO4 kind of just like floating around in the mixture. So this is going to interact with this bond here. So it's going to grab the Hg2 plus, which happens to be our Lewis acid, and then this is our Lewis base. So we end up with a positive charge on this carbon. And that's when water comes out. Actually, before I go through all this, did she say if you were going to have to know the mechanism for this specifically, or just the tautomerization? Let me check the homework.
I was on Carrie's office hours yesterday, and she said this one, but Carrie, if you watch this, I'm sorry if I'm wrong. But yeah, so it sounded like she was really serious about this, but I don't know. But that's just what
Okay. Let me just double check. Did she go through this on her video?
Yeah, she talked a lot about hugs, and
Hugs.
yeah, she's like, there's the hug, and then it comes, and then it offers you water, and then it was really good. It was anyway, if you get a chance to watch it,
Yes.
it was really cute in the ways in which I like stuff like that.
It sounds very Carrie.
Yes. So very much like, it's a good host and he gives you water, but then there's too much water, so then it goes away because it's mad. It was really cute.
Well, I'll do this one and then I'll do the other one because I'm really not sure if you're supposed to know like this whole mechanism or not, but let's do it. So Hg gets added first to the alkyne, right? So the bond is going to grab hold of that. We're going to have a positive charge on that carbon. Water is going to come in. Time to hang out. And we always want to label our Lewis acids and our Lewis bases. So now we've got this looking thing. And water is going to come in again and deprotonate. Boop. So let's do it up. And so we've made hydronium, so hydronium is going to come in again. And the Hg is going to snag a hydrogen and break these bonds. Oh, not the Hg. Hold on a second. Sorry. Not reading my lines correctly. So this bond is going to grab the hydrogen. Hg is going to leave though. Goodbye. Now we've got 2 hydrogens and we've got that alcohol group. So we call this an enol. Sorry. I might have to finish this later. I have another meeting that I have to get to. Do you guys mind if I could either go over this tomorrow or I can make a video after my meeting, but I do have to go.
Tomorrow's fine, and don't forget to plug in your laptop.
Oh, yes, thank you. My iPad is at 22%. So I'm going to go ahead and stop recording. I'm sorry we didn't get through the whole thing.
I'm